the work done in an isothermal reversible process is greater than the work done in an isothermal irreversible process. That is what I am supposed to explain you in this class just now. Okay. Now, we already know the formula for work done in a reversible process. It is minus 2.303 nRT log to the base 10 P1 by P2. Now, if you look at this graphical representation of the irreversible work over here, this A, B, C, D, this area enclosed between A, B, C, D, if it is plotted, it is the work done in an what you call reversible process. Work done in an what you call reversible process. That is area of A, B, C, D. But the work done in an irreversible process is A dash, B, C, and D. So you can see the area covered by capital A, capital B, capital C, and capital D is greater than the area covered by A dash, B, C, and D. So from this it has been proved that the irreversible work is smaller, it is lesser than the reversible work. Okay, so this graphical representation you must try to remember. Now this figure 6.6 is the graphical representation of reversible work. Okay, so here you can see for reversible work, the area covered, it's big. It is big. You can see the black strip EFGH for any infinitesimal amount may be regarded as a rectangle of area PdV. Okay, so that's why we can say that the work done in a reversible process, isothermal, is higher than the work done in an irreversible process. Okay, so after this, we can move to the energy changes during different chemical reactions. This is an important part of the chapter. Now, what are the energy changes happening in a chemical reaction? To understand this, let us first try to understand the first paragraph over here. The formation of a chemical bond, when a chemical bond is formed, it is always accompanied by a decrease in the potential energy of the system. So remember that when a bond is being formed, the potential energy is decreased. It is lowered. This implies that the energy is released during the formation of a chemical bond. So try to understand this. So whenever a chemical bond is formed, energy is given out. Moreover, we have also seen that a definite amount of energy is needed to break a chemical bond. So in order to break also, we need to provide some energy to break it. In a chemical reaction, reactants combine together to form products. The formation of products from reactants demands the breaking of some or all of the old bonds and the formation of new bonds. So whenever new bonds are being formed, remember there is decrease in potential energy of the system. So here you can take an example, burning a methane in oxygen to form carbon dioxide and water. So here the bonds between carbon and hydrogen and methane are completely broken, as well as oxygen, and it is forming carbon dioxide and water. So you can see by this illustration. So here, thus a chemical reaction always involves the rearrangement of bonds existing between the atoms of the molecules of reactants to form the molecules of the products. Now remember, the bond energy varies from one bond to another. There must be an energy change when products are formed from reactants. This is why a chemical reaction is always accompanied by a change in the energy of the system. So remember, there might be either absorption of energy or evolution of energy. So whenever there is a chemical change, or a chemical reaction happening, it is always accompanied by an energy, change of energy in the system. So based on this, the chemical reactions are of varied nature and involve various forms of energy, which will be discussed now. The first one is heat energy. If you try to go through this in depth over here, the reaction in which it is given out, we already know it is an exothermic reaction, but the reaction in which heat energy is absorbed, it is called endothermic reaction. So here, look at this reaction. Carbon plus oxygen is forming carbon dioxide, and over here plus sign is given for the heat which is given out. Okay, it is an exothermic reaction. So the heat energy which is given out, we are putting a plus sign on the product side. okay, for an exothermic reaction. But if you look in the case of endothermic reactions, for in order to this nitrogen and oxygen to combine, we need to provide so much kilocalories of energy so that they combine. Same thing goes for during the formation of ethanols. We need to provide minus 53.1 kilocalories of energy so that carbon and hydrogen combine to form ethane. The other form of energy is light energy. Several chemical reactions involve the absorption of energy in the form of light. Now, such reactions, definitely they are called photochemical reactions. Examples are given over here. Combination of hydrogen and chlorine. Reaction of sulfur dioxide and chlorine. Okay. Solve photochemical reactions. Light may also be emitted. These are using light energy. But there are other reactions like if you take, if you expose phosphorus to the air, oxygen of the air, it forms phosphorus pentoxide, but light energy is given out. Both light and heat energy may be evolved simultaneously in a reaction like this. If you take magnesium ribbon and you burn it in oxygen, so both heat is given out as well as light is given out, bright white light. And the third one is mechanical energy during chemical reactions. Now, there are compounds like gasoline. If you burn it in an internal combustion engine, it produces a lot of heat energy. It produces, because of which mechanical energy is processed. And this mechanical energy can be used for a variety of purposes, for turning wind, what do you call it? For turning turbines, what do you call this? Energy pistons and all, okay, and we can make some work done over there. Then the fourth one is electrical energy. Cells like battery, Daniel cells, galvanic cells, like cell, dry cell, produce electric energy on account of chemical reactions happening in them. So these chemical reactions are basically of the type of redox reactions. So if you look at this reaction, when you place a zinc rod in a copper sulfate solution, then there is movement of electrons. Movement of electrons taking place from the surface of zinc metal and going and combining with the copper ions, entering the copper ions valence shell to form copper. So that movement of electrons from the zinc metal to the copper ions, it is producing some electrical energy which can be harnessed in the galvanic cells for providing power. Okay. Now we come to the next part of the chapter, which is called first law of thermodynamics. Over here, before we understand the first law of thermodynamics, please remember this thing over here. All processes occurring in the universe involve the conversion of energy from one form to another. We cannot produce energy or we cannot destroy energy. We can neither produce nor destroy energy by any means. Simply we can change energy from one form to another. This is the main concept, basis of the first law of thermodynamics. For example, an electric generator in true sense does not generate electrical energy. It simply converts the mechanical energy obtained by the combustion of fuel into electrical energy. When electric current is passed through a bulb, the electrical energy changes into light energy and heat energy. Thus, a particular kind of energy is produced only when an equivalent amount of some other kind of energy disappears. Okay, this observation finally led to the formulation of very first most important law, which is called first law of thermodynamics. So, if you look at the various statements for the first law of thermodynamics, we can see energy can neither be created nor destroyed, although it can be converted from one form to the other, various forms. The second one is the total energy of an isolated system remains constant, although it may change from one form to another. Third one, the total energy of the universe is constant. Fourth one, whenever a quantity of some matter, some form of energy disappears, an exactly equivalent amount of some other form of that energy must be produced. Number five, for a system in contact with its surroundings, the sum of the energies of the system and the surroundings at a particular moment remains constant. However, howsoever differently it is shared between the two. Number six, we cannot construct a machine, a perpetual machine, that is a machine which would produce work continuously without consuming energy. That is impossible thing. So these were some points over here on which the first law of thermodynamics has been stated. Okay. All the above statements, they mean the same and implies that we can neither produce nor destroy energy. So justification has been given over here for the first law of thermodynamics by the following observations. Till now, we could not construct a machine which is 100% efficient. So the second one, on supplying 26 kilojoules of energy to 1 mole of water, it decomposes to give 1 mole of hydrogen and half a mole of oxygen. That is very, very true. Okay. Then after that, come down to internal energy and internal energy change. Now, what is internal energy? Let us understand that. I was telling you roughly in the previous classes that the energy content of a substance or any body is the internal energy. If I do work on a substance or a body, I am going to what? Increase the internal energy. But if the system does work on the surroundings, then there is a decrease in the internal energy of the system. So on this basis, let us try and understand the meaning and the concept of internal energy and internal energy change. Now, as discussed earlier, the physical and chemical changes are usually accompanied by energy changes. The evolution or absorption of energy in a physical or chemical change is possible only when a substance is associated with a definite amount of energy. In fact, this is true. Every substance is associated with a definite amount of energy known as internal energy or intrinsic energy. So, better try to remember the other form of this word internal energy, which is also called intrinsic energy. Now, the symbolic representation for internal energy is either capital U or capital E. Now, a substance may be associated with different types of energies such as translational energy on a straight line UT, rotational energy, okay, UG, vibrational energy of the molecules UV, electronic energy UE, nuclear energy UN, molecular interaction energy UL, okay. Internal energy is actually the sum of all possible types of energy associated with the system or the atoms or molecules of the given substance. It is a thermodynamic function. It is a function of thermodynamics and it is represented by capital U or capital E. However, in this book, we will be strictly following the symbol U, which is used for internal energy. Okay. The total amount of energy associated with a fixed amount of a substance under a given set of conditions is referred to as the internal energy or intrinsic energy of that substance. So here you can see translational, rotational, vibrational, nuclear, okay, all those energies are here. Okay, so that is the definition of point energy. Now after that, the more important term over here is internal energy change or delta U or delta E. Now we know internal energy is a state function. It is not a path function. It does not depend on the path. Now it depends on the state of the system and not upon how the system attains that state. This means that a change in the energy depends only upon the initial and final states of the system and not upon the intermediate states. Therefore, while determining the value of delta U, we are not concerned with the path or the way by which a system transits from one step to another. The change in internal energy is defined as a difference in the internal energies of the system in the final and the initial state. So there is equation 6.9. So delta U is equal to U final state minus U initial state because it is a state function. It is not a path function. Now, when a chemical reaction occurs, normally the internal energy of the system before the reaction is usually different from the internal energy after the reaction. So here, this is because the nature of the molecules of products obtained in the reaction is different from that of the molecules of the reactant. So that's how we write over here. Delta U is internal energy of the products minus internal energy of the reactant. So delta U is UP minus UR. Okay, that is easy. Now from this, after this concept, after understanding internal energy, then only formulate, we can formulate mathematically the first law of thermodynamics below. The internal energy of a system can be changed in the following two ways, either by allowing the heat flow into the system or allowing the heat to flow out of the system, or by the work done on the system or work done by the system. So there are two possibilities over here. Okay, so based on this, if you consider the internal energy of system under a particular set of condition to be U1, This will, and then after that, suppose the Q amount of heat is supplied given to the system. We are supplying heat to the system, giving heat. This will increase the energy of the system. So U1, it becomes U1 plus Q because you are giving Q amount of heat. Now, if work W is done on the system, the energy of the system will increase. So we have a final state U2. U2 means what? U1 plus Q. So U2 minus U1 will give us Q plus W. Or you can say U2 minus U1 is delta U internal energy change is equal to Q plus work done. So this is the formula relating internal energy, the heat supplied or given out, and the work done on the system or work done by the system. Okay. Now we can also say change in internal energy is heat supplied to the system plus work done on the system. So this equation provides a relationship between the change in internal energy of the system, heat supplied to the system, and work done on the system, and is regarded as the mathematical statement. So this will be the question in the examination. Write down the mathematical statement of the first law of thermodynamics. So you better write this equation: delta E or delta U is equal to Q plus W, assuming that work is done on the system. Okay, so using equation 6.11 can come to some conclusions, derive some conclusions. Say if work done is 0, then the change in internal energy is equal to the heat supplied. That means if no work is done on the system, the change in internal energy is equal to the heat absorbed by the system. Okay, that is the first case. If internal energy change is 0, then Q, the heat supplied, is equal to negative work. Okay. If the work done is the work of expansion, okay, the gas is expanding in a container. So that time the work done is minus P delta V. So if you substitute the value of equation 6.11 in place of W, you put equation 6.11, then we have delta U is equal to Q minus P delta V. Q comes this side. So we get equation over here Q is equal to delta U plus P delta V. Okay. If the process is carried out on a constant volume, then the volume becomes 0. So we can have QV at constant volume, that is equal to change in internal energies, where QV signifies the heat absorbed by the system at constant volume. Now this equation 6.13 implies that under constant volume and constant temperature conditions, the change in internal energy of the system is equal to the heat absorbed by the system. Hence, delta U is regarded as a measure of heat absorbed or evolved in a process occurring at constant volume and constant temperature. So remember, but on the contrary, remember Q and W are state functions. Neither Q nor W are state functions. Yet, if you add them, Q plus W, you're getting delta U, which is a state function. So, the sum of two path functions, it is giving a state function. Okay. So, based on this relationship, based on this concept of delta U is equal to Q plus W, we are going to derive a relationship between heat capacity at constant volume, that is CV, and internal energy, that is delta U. So molar heat capacity comes into play over here, where it is at constant volume is defined as the amount of heat required to raise the temperature of 1 mole of any substance or a gas by 1 Kelvin at constant volume. So on this basis, this CV stands for heat capacity at constant volume, that is equal to QV by dt. This formula you have to remember. Derivation for this is not required. Now QV is an infinitesimally small amount of heat absorbed by the system at constant volume to raise its temperature by dt, small amount of temperature. So we can have QV is delta U. Since we know QV is delta U at constant volume and constant temperature, at constant volume only, so we can substitute these values over here. CV is equal to delta U by delta T at constant volume. Okay, or write it in this form. Okay, then thus, heat capacity at constant volume may be defined as the rate of change of internal energy with temperature at constant volume. Okay, so remember this sentence. Then, internal energy change, work done, and heat absorbed in a cyclic process. In a cyclic process, the heat absorbed. When initial and final state of system are the same, the process we know it is said to be cyclic. In a cyclic process, the system undergoes a series of changes and returns back to its original state. Since internal energy and enthalpy are state functions, in a cyclic process, remember, the reason is here. In a cyclic process, the internal energy and enthalpy are state functions. That is why the change of internal energy and enthalpy change, it is 0. So we know according to first law, delta U is equal to 0, that is Q plus W. So we can say Q is equal to minus W. Okay. The reversible cyclic processes are theoretical and imaginary, yet they are very helpful, meaningful in understanding the work of a heat engine. From this point of view, very important cycle process, Carnot cycle, has been explained in this chapter. Okay, now there is one example over here. Just try to go through this example on your own. State whether each of the following will increase or decrease the total energy of the system. So heat transfer to the surroundings. What will happen? If the system is transferring heat to the surroundings, what is happening to the internal energy of the system? Tell me. If the heat is being transferred to the surroundings by the system, what will happen to the internal energy? Will it increase or decrease? Will it increase or decrease? Tell me. When the heat is transferred to the surroundings, what will happen to the internal energy or energy content of the system? Will it increase or decrease? Yes, you can see the answer here only. It generally decreases. It generally decreases. The second one, work done by the system. If the work is done by the system, then the system is using the energy. There is loss of energy in the form of work. Hence, total energy content of the system decreases. That means internal energy is also decreasing. The third one is work done on the system. We are doing work on the system, providing work to the system. So in the third case, when work is done on the system, involves a gain of energy. Hence, the total energy content of the system also increases. Number four is heat transferred from surrounding to the system. From the surrounding, we are giving heat to the system. So again here, the total energy content of the system also increases. So based on this, some simple numericals are required. Some simple numericals are required. Okay. Mathematical form of enthalpy I have already told you. Okay. So here, this numerical, if you see a system is absorbing 400 joules of heat and does work equivalent to 150 joules on the surroundings, is giving heat outside. Calculate change in internal energy. So the formula you apply directly. Because its work is done by the system, that's why work is minus. And heat absorbed by the system, so Q is 400 joules plus 400 joules. So let's put the formula directly. Delta U is Q plus W. So 400 plus minus 150 will give you 250 joules. Okay. So this is how you get the answer for internal energy change. Similarly, practice example 6.3 also. The gas is expanding against a constant pressure. Pressure is constant at one temperature. From volume of 5 liters, it is expanding to 10 liters. So there is change of volume, V2 minus V1. Okay, this is work of expansion. So during the process, system absorbs 400 joules of heat from the surroundings. So we are supposed to calculate, use this formula. Work done is minus P delta V. Pressure is 1. Volume is changing from 10 to 5. It is coming to 5 liter atmosphere. Okay. And we know 1 liter atmosphere, learn this value. 1 liter atmosphere is equal to 101.3 joules. So instead of this liter atmosphere, multiply over there 101.3, you will get the answer in joules. Okay, for work done. And also from the first law, we know internal energy formula delta U is equal to Q plus W. So put the values over there. It is absorbing 400 joules of heat. So 400 plus minus 506.5 will give us minus 106.5 joules for internal energy. Okay. So here keep in mind that it is the gas is expanding. The gas is doing work itself. So there is a negative sign over there in the case of internal energy. Okay. Similarly, practice 6.4 also. 6.4 it is there. Practice it. It is pressure volume work. Then enthalpy, H and enthalpy change. Enthalpy. The next word in this chapter is enthalpy and enthalpy change, that is delta H. Now, what is enthalpy? The heat change. Enthalpy, the symbol is H. Now, the sum of the internal energy, if we add the internal energy and the pressure volume energy of the system, that is called enthalpy. So, try to learn this formula. The sum of the internal energy and the pressure volume work, it is called enthalpy. And also, enthalpy is a state function. It doesn't depend on the path. Therefore, the change in enthalpy depends only upon the initial and the final states of the system, like this. So delta H is H of products minus H of reactants. So this you remember. And you can just do some manipulation with this formula. Delta H is equal to delta U plus delta PV. Okay, and expand this. If a change takes place at constant pressure, this P becomes zero. This becomes zero. So we have only delta U plus P delta V. Okay, at constant pressure. Okay, delta is equal to Q plus V, W. This P delta V means work done. Okay, if the work done is at work of expansion, that means it is expanding. W is minus P delta V, and we have delta H is equal to Q minus P delta V, expansion of work. The system is doing work on the surrounding in this case. So if you substitute the values, you can get a final relationship. Delta H is equal to QP. Energy refers to the heat change occurring at constant pressure. Okay, so this you try to remember. And then relationship between delta H and delta U. Learn this relation directly. Delta H is equal to delta U plus P delta V. Okay. Then working with this relationship over here, PA, the ideal gas equation, volume of gases, reactants, and VB with the total volume of gases products. Na is the total number of moles of gases reactants, and B is the total number of moles of gas products. So according to the ideal gas, we can write two equations over here. PVA is equal to NART, PVB is equal to NBRT. So equating them, okay, subtracting them, V2 minus V1, PVB minus PVB is equal to NBRT minus NART. So we get this form, P delta V is equal to delta N RT. Okay, so this is one form. Okay, and delta N, we know it is summation of the number of moles of gaseous products minus summation of the number of moles of the gaseous reactants. And then putting in the above formula, delta H is equal to delta U plus delta, because we know P delta V is delta nRT, so put it over here and we get this. So we have various cases. When delta N is 0, delta H is equal to delta U. When delta N is negative, that means delta H has to be less than delta U. Well, delta N is positive, then delta H becomes more than delta U, internal change. Okay, so based on this, we have one more equation, 6.22. QP is equal to QV plus delta nRT. Okay, so this you go through the conditions under which delta H equal to delta U. Examples here, one condition is there, second condition is there, third one is there. Okay, these three conditions will be sufficient, and now based on the formula, delta N is equal to summation of delta N gas products minus delta N gas reactants. There's a numerical over here. The enthalpy change value is given minus 92.3 kilojoules per mole at 98 Kelvin. So what is the value of delta U? So first get the value of delta N. It will become, this is 2 over here, plus 1 plus 3, minus 1 plus 3, this is coming to minus 2. Delta N value is minus 2. Okay, so write this equation, delta is equal to delta U plus delta N RT, and put the values. So upon putting the values, you will get the value of delta U, that is internal change. Similarly, practice example 6.6 also. 6.7 is also there. Okay. 6.8 is also there for a bomb calorimeter, which I've learned in class 10 physics. Okay. Then applications of first law of thermodynamics. This I will do in the next class. Okay. Application of the first law of thermodynamics, that is from the Joule-Thomson effect. I will complete this in the next class. Okay. So from here I will do in the next class. So first let me take the attendance, then you may leave the class. Okay.
Yes, sir.
Attendance is downloaded. Okay. So now you may leave the class. Thank you so much.
Thank you, sir.